Hello, I'm Michael Irani, and I am talking to you from Los Angeles. The topic today: demystifying Chrome OS crashes. Just two housekeeping items before we get started. First, please provide any questions you have on the Slido. There's information on the top right of your video. And then for non-Googlers, I do discuss crash dashboard that you do not have access to. I hope the content of this talk is useful to you, regardless. A little background about myself. I'm on the Chrome OS telemetry team, and we are responsible for the crash reporting system on Chrome OS. We make extensive use of tooling built by the Chrome crash team, led by Ivan Penkov. And when I talk to developers about crashes and how we're responsible for crash reporting on Chrome OS, I get one of three reactions. Either we have the expert developer of Chrome OS who offers a new great way of reporting crashes on a new dashboard that will make our triaging efforts easier. There's a second type of developer who doesn't have one, just thinks things are working fine. And then we have a third type of developer who's usually newer to Google or newer to Chrome OS development, and their thoughts on crashes on Chrome OS is that it's something like they'd rather not do. It's a scary thing that they don't really know how to triage them. They don't know how to fix crashes, and they're looking for other people to help them out. I just want to relay a quick story. So when I was in high school, I was very much into wrestling. It was something I was passionate about. I loved competing in tournaments. And then when I entered real life, at least in LA, there's nowhere I can go to a gym and compete at wrestling. So people had suggested to me, you should go into BJJ. Jiu-jitsu is really close to wrestling. It's the same type of idea. You can use your grappling, your experience to be a good practitioner of BJJ. And for years, I thought about going, but it didn't go because it seemed like a scary thing. One day, I finally went to the gym, signed up for a 1 month pass, stepped on the mat, and went for my first class. I found it exhilarating. My wrestling technique was useful in this new art, and it was actually interesting to try out new ideas that are different from wrestling but similar in their own way. And getting back to crashes, if let's say you're formerly a Python, Ruby, Java, JavaScript developer, you have the skills to dissect and fix crashes. It's just a matter of learning some new language and tooling to help you dissect and fix crashes in Chrome OS. Let's jump into the slides. So when you join Chrome OS, what is your introduction to crashes usually going to be? It's usually going to be an email that looks like this, which will drive you to a bug report that looks like this, and then you'll be led to this great crash report, and you'll have no idea what to do. And what will you do? You'll look around for some seasoned developer to hand off the bug to, so that you can move on with your day. So now let's take a step back and really think, like, why is this whole prospect of triaging crashes so anxiety provoking? It's because we don't really, there's some language and tooling that we don't know about yet. So let's just get us all up to speed. So first, what is a crash? A crash is a process, system, EC, or firmware crash. This includes browser, UI, journal, JS, kernel, ARC++, and cross-any crashes. So if a process crashes or a current crashes, we get a crash report, and that's what we're discussing. So another important thing to know about is a magic signature. So magic signature, let's read through the definition. A magic signature is a Chrome-specific property used to bucket crash reports. It aims to incorporate application-specific knowledge about the crash to do a better job at labeling the underlying cause than the generic stack in your property. So what this means is the Chrome crash team has built this really great tooling that tries to take crashes and cluster them in better groupings. And the idea is, let's say we had 1,000 crash reports total, and we were forced to look through every single crash report individually. That would be a lot of work to do. It'd be kind of hard. So ideally, we'd have the perfect clustering where each group of crash reports was the same type of crash. So we'd have, let's say, 10 bugs, and each one of them was a specific issue. And one of the things I want to highlight with respect to magic signatures is that the magic signature, while it's a great technique, it's not perfect. So there are many cases where one magic signature will actually be connected to many different types of crashes. And it's important to look through the stack, especially at the bottom, to see if where this crash originated from matches up with the crash of another bug that's already assigned to the magic signature. And we'll go through a couple example later on. And while we're on the topic of magic signatures, let's talk through some of the non-actionable signatures. So if you see the signature, it's hard to know how to address the crash. One is a TC malloc corruption. And what this means is that some other part of the system at some point, another part of the program, has already corrupted the heap. So when you get to this, to your current stack, to your current crash report, the information that you're looking at doesn't help you dissect why the heap is corrupted. It's already been corrupted before you got to this issue. Another non-actionable signature is the EPAL dispatch. And then once again, this is outside the control of the stack that you're looking at. It was caused by the device being too busy, so looking at your stack won't really let you know how to address the issue. And another class is a prefix, actually. So if you see shutdown hang something, this means the thread terminated during shutdown because it took too long. So once again, it's not the cause of your code, but something outside your control, so it's hard to address these issues. Moving on, another thing to know about is the crash report itself. So in the crash dashboard, you'll see this is the main page. This is the summary page, and there's a couple things I'd like to highlight. So first, we have the report ID. So this is a unique ID per crash report that will let you come back to this crash report. There's the magic signature that we already discussed. There are links to bug reports related to this magic signature. There are files that were collected as part of this crash report. And also at the bottom, we'll see the stack trace, which is a really important piece of information when trying to diagnose crashes. And then at the top of the stack, you'll see there's a signal, the SIGSEG-V, and we'll get really deep into different signals and what they mean and how they can help you triage crashes. Now, another important thing to know about is that crash reports are categorized into three main ways. So these are just labels that are put in the crash reporting dashboard database. Chrome OS crashes are usually lower level Chrome OS system crashes. Chrome OS crashes are browser crashes, GPU crashes, render, utility crashes. And lastly, the Chrome OS ARC crashes are ARC++ crashes. So sometimes when you're filtering the crash dashboard, you might think that filtering by Chrome OS will give you all the crashes. Once again, that is not true. You will not be seeing many of the crashes from Chrome OS. And another important thing to understand is how we think about crashes. How do we think about crash severity? And the metric that is most used across Chrome OS today is CPM, crashes per million page loads. What this means is in the Chrome browser, how many pages were loaded across all our systems. While this isn't a perfect metric for an OS, this is the most widely used metric today. We are planning maybe to change in the future, but for now, this is the metric to most know about, because if you look at different dashboards, this is the metric you will see. And then the other thing that I've lightly talked about before is that you want to know and look at the stack trace, and you'll see the stack trace listed on the summary page at the bottom, as well as if you click on the threads tab, you will see the stack trace. Okay, let's talk a little bit about why we should invest time in fixing crashes. First, the user experience. As an end user, I'm sure you've experienced when a process or a system crashes. It's a jarring experience. It's something we don't want users to experience. So anything we can do to alleviate any stability issues for end users, we will try to take care of. A small volume of crashes with considerable CPM, meaning just if we were to address the top crashes across the system, we'd have a huge impact on the overall CPM for Chrome OS. And lastly, if we have crash reports in the system that aren't actionable, they aren't user-facing, they flood the system, so it's hard for us to address the actual user-facing crash reports. We want to keep the system as clean as we possibly can. For example, last week, we had a crash, a magic signature that showed up that made up for about 70% of the crash reports that were collected for a certain version of Chrome OS. Now, these were completely not user-facing and no impact. It was a non-issue as far as the user goes, but it completely flooded our system, so it was hard for us to notice real crashes that were really impacting the user. So we want to try to keep the system as clean as we possibly can. Okay, now let's get into the crux of the talk. How do we triage crashes on Chrome OS? There are four main areas that we look at. First, at the top of the crash report page, the associated bugs. At the top of the stack trace, we saw the crash signal. At the bottom of the page, we saw the stack trace. And then there are also log files that we collect as part of the crash reports. Once again, from the beginning of the deck, you will get a bug. It'll have a link to the crash dashboard. We'll then get to the crash report page, and we'll see a bunch of bugs that are linked at the top. So what we want to do as a developer is we want to look at the bugs that are associated with the magic signature and try to look if the bugs that are already opened match up with the crash report we're looking at on that day. Do the stack traces look at the same? So you want to look at the bottom of the stack. Does the stack of my crash report match the stack trace of the crash report that's linked in the bug? And also, we'd want to look through the bugs and see what's already been discussed to understand if the crash report we're looking on matches up with what's there already. Another thing, as we mentioned already, is the crash signal. In the next section of this deck, we'll walk through a couple different signals, what they mean, and examples of fixes to these crashes. Third, we want to look at the stack. So if the stars are aligned and you have a mini dump and the source map for your crash report, there's going to be another tab that'll show up, which is kind of magical. It'll show on the left side the stack trace, and on the right side you will see the actual code that was built for that version, along with like basically a git blame. It'll tell you who changed those lines of code and when, and sometimes you'll see that the crash happened at a place that was modified within like a week or a couple of days. So obviously you'd want to get that person involved because they might have an idea as to what happened with this specific crash. And then lastly, I just wanted to mention that you may want to download some of the files that are collected as part of the crash report. There is a files tab that will show you some files. But one issue is that you cannot, if the file that was uploaded with the crash report is compressed, the crash dashboard does not decompress the file for you to read it. So you want to download it, decompress, and then read it. And then let's talk about when to create a new bug. So first off, let's say you're looking at a magic signature and there are no crashes associated with that magic signature. You may want to create a new bug. Or if there are other bugs already associated with this magic signature, is this crash report a different type of issue than the ones that are already addressed? When we're creating the bug, we want to try to find an appropriate person to assign the bug to. And also, if you learned anything while you were looking through the crash report, please add that to the bug. And after you create the bug, please associate the bug with the magic signature so that we reduce the number of duplicate bugs we create around crashes. And now I just want to thank Vlad Kazanchev for providing me with a couple examples that we could work through. So these are real life examples that I took the smallest bit of the change to really just elucidate what the issue is and what we were trying to fix. So the first signal that we're going to talk about is SIGSEGV. So this is a segmentation fault. The definition, an invalid memory reference or a segmentation fault. What this usually means is that there was a null pointer dereference. The first example is pretty straightforward. There was a refactor for the multi-profile use case, and secondary users would be in a situation where this Kerberos credentials manager object would actually be a null pointer. So when we hit this code, we'd have a null pointer dereference, and then we'd be trying to be calling a member function on a null pointer, and the SIGSEGV would happen right there. So all that had to happen is to check if we have a null pointer before we try to call the member function, and the issue is addressed. Another example of SIGSEGV is here we had a callback to this Arc app shortcut search result object. And what could happen is that the callback may outlive the object. So what we had to do is introduce a weak pointer factory so that when the Arc app shortcut search result object is destroyed, it will also cancel the callback. I mean, part of the going through these examples just show how tiny of a change we're potentially talking about to fix these crashes. So now we're going to talk about the next signal, which is a sig trap. This is a signal sent when a condition a debugger is requested to be informed of occurs. So if there's a check or a log condition that fails, then we will get this crash report. And for these cases, you may want to download the file to look for the check failure. So here's a really straightforward example. So there's a bit of code that looks for this condition. If this condition is not met, then the crash report is generated. All that had to happen is instead of having the check, it was just to handle the null pointer case appropriately. And in that case, if that were to exist, we just skip this code and handle it without any noise. And now we're going to talk about the next signal, which is a sig-il. It's an invalid program image, such as an invalid instruction. The most common causes are a check failure on some platforms, a corrupted stack, using a vtable of a corrupt or destroyed object, or a bad function pointer. And once again, for sig-il, you may want to download the log files to look through them for check failures. Here's a pretty straightforward example once again. So here we have an attempt at casting to an inappropriate type. So all that had to happen is to remove the static cast, and the issue was resolved. And then this example I kind of like. So here we have the TTS handler, which is the text-to-speech code. So the TTS handler never removes itself as an utterance from the delegate in this destructor. So the issue is that utterance is alive, but the TTS handler gets destroyed. So in that case, any calls to the TTS utterance on TTS event would dereference a deallocated TTS handler. So all that had to happen for the fix is for the TTS handler to remove itself as a delegate in this destructor. All right, on to the next signal. So this one is a pretty straightforward one to understand. It's a sig abort. So this is an abnormal termination condition. This is often caused by an outside actor sending the signal, such as the session manager on Chrome sending a sig abort. And I think this example is really quite clear to follow. So what happened here is on system shutdown, we have 3 seconds for this process to collect what data it needs and terminate itself. And what was happening is that there was a race condition where the 3 seconds of this process trying to do its work, may not have aligned with the actual system shutting down. So sometimes the system was sending a sig abort signal to this process to terminate. The fix was just to reduce the timeout to 1 second so that the process would shut down itself without the system having to do it. Another crash signal to just mention really quickly is the dump requested. This is the result of a developer putting in a dump without crashing. So this is basically the developer is interested in getting some information about the process without actually causing any crash. So the user doesn't impact the user experience in any way, but it's just a way to get basically debug information. So this is once again not user impacting, but if this spikes, we want to look into it. And in conclusion, once again, just want to highlight that the crash reporting world is not all that scary. It's just a matter of understanding how crash reports, what's in a crash report. And we highlighted associated bugs, looking through the error signals, looking at the stack trace, looking through any associated logs. Once again, I want to highlight the magic signature clustering is not perfect. So we want to look through the bugs that are associated with magic signature, see if the crash report we're looking at is part of any bug that's already there, or should we introduce a new bug? And then the metric we use by default in Chrome OS is CPM. So it's good to understand the different thresholds as to which ones we should consider. And now let's look if there are any questions. Okay. 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 Okay, the question is, what blind spots does the crash reporting system have? This is a great question. We're actually focused on a couple efforts in this space right now. One is to capture web UI JS crashes, and Ian is actually working on this right now. So, Ian, you want to take it away?
Sure. As the question says, we want to capture JavaScript issues. Right now, we do have some issues with JavaScript pages that built-in JavaScript that gets exceptions or errors, and we don't really know about it. Um, only on like Chrome pages, obviously. Um, Otherwise, yeah, there are a few other uh, small blind spots. That's the big one. I think that's the main one. There are obviously occasionally really bad system failures, which we're never going to be able to get a hold of because it forces the system to just be power washed or whatever. We're obviously never going to be able to capture those because it'll erase the system.
Um, sure. If there are no other questions, thank you so much for joining and learning about crashes on Chrome OS. We really see a bright future ahead. We're working on lots of projects to try and make it easier for developers to see crashes and address issues and to see metrics over crashes. And if there's anything we can do to help, please reach out. My email is michaelirani@google.com. And just, we're here to try to make Chrome OS a more stable operating system. Thank you.